Hello and welcome to Alpha Omega General Training videos. In this tutorial, we will be learning about magnetohydrodynamics modeling using Ansys Fluent. Ansys Fluent is a powerful computational fluid dynamics tool that provides advanced capabilities for MHD modeling. Whether you are a skilled student, researcher, or engineer, this tutorial will assist in enhancing your expertise in this field. So, let us begin exploring the intriguing realm of magnetohydrodynamics modeling. Magnetohydrodynamics is a critical field of study that combines electromagnetism with fluid dynamics. Ansys Fluent provides a comprehensive platform for MHD modeling, allowing researchers to simulate and analyze various phenomena where the flow of an electrically conductive fluid is influenced by a magnetic field. In Ansys Fluent, MHD equations are solved using a coupled, implicit method that ensures a high level of numerical stability. The software offers a range of models to simulate incompressible and compressible flows, laminar and turbulent flows, and it includes the effects of Joule heating and electric body forces. These comprehensive features allow for the accurate simulation of complex MHD scenarios such as plasma flows, electromagnetic stirring, or magnetic confinement in fusion reactors. Ansys Fluent's MHD capabilities combined with its robust meshing techniques and parallel computing capabilities make it an invaluable tool for researchers and engineers working in fields where MHD effects are significant. Magnetohydrodynamics involves the study of the dynamic of electrically conducting fluids such as plasma, liquid metals, and salt water. In the field of power generation, MHD is applied in MHD power generators, which are unique as they don't require moving mechanical parts. MHD power generation is a direct energy conversion method, converting thermal or kinetic energy directly into electricity. It operates on the principle of Faraday's law of electromagnetic induction, where a conductor moving in a magnetic field induces an electromotive force. In an MHD generator, the conductor is a hot ionized gas or plasma. The main advantage of MHD generators is their high thermal efficiency, potentially reaching up to 60%. They can be integrated into conventional power plants to increase overall efficiency. However, there are challenges such as electrode material degradation and the need for a high temperature ionized gas source. Despite these challenges, MHD power generation holds potential for future power generation, particularly in applications requiring high power and efficiency, such as space propulsion. Further research and development in this field could lead to significant advancements in sustainable and efficient power generation. The study of the interactions between magnetic fields and conducting fluids has significant applications in the field of metal processing and casting. It's used to control the flow of molten metal in continuous casting processes, enhancing the quality and uniformity of the final product. The application of MHD in metal casting provides a non-contact method to manipulate the molten metal, which is especially beneficial in handling high temperature and reactive metals. MHD can mitigate turbulence, reduce defects and inclusions, and promote directional solidification. In the context of electromagnetic stirring, or EMS, MHD is employed to stir the molten metal, promoting homogeneity and reducing microsegregation. MHD is also used in electromagnetic braking to control the speed of the molten metal, reducing surface turbulence and improving the surface quality of the cast product. Moreover, MHD is applied in electromagnetic casting, a process where the molten metal is directly cast into final shapes under the influence of magnetic field. This process reduces the need for subsequent processing steps, saving energy and resources. MHD thrusters or magnetoplasma dynamics utilize the principles of MHD to accelerate plasma for propulsion, offering high specific impulse and thrust efficiency. The primary working mechanism of an MPD thruster involves the interaction of electric and magnetic fields. An electric field generated by a voltage difference ionized a propellant into plasma. This plasma, being an excellent conductor, allows a current to flow. The interaction between this current and an applied magnetic field creates a Lorentz force which accelerates the plasma out of the thruster, generating thrust. MHD propulsion has the potential to revolutionize space travel, especially for long duration missions. It offers a higher exhaust velocity compared to traditional chemical propulsion systems, which translates into more efficient fuel usage. However, challenges persist, such as the requirement of high power input and the difficulty of achieving stable plasma states. Despite these challenges, ongoing research and advancements in power generation and plasma physics are paving the way for the practical implementation of MHD propulsion in future space missions. The MHD model in Ansys Fluent is a powerful tool for simulating flow and heat transfer in electrically conducting fluids under the influence of magnetic fields. This model is based on the Navier-Stokes equations coupled with Maxwell's equations, which describe the behavior of electromagnetic fields. In Ansys Fluent, the MHD model is implemented through the solution of momentum, energy, and electric potential equations. The model takes into account the Lorentz force, Joule heating, and the induced magnetic field. The MHD equations are discretized using a finite volume method and solved iteratively. Here are some of the features of MHD model in Ansys Fluent software. Simulation of electromagnetic fields. The MHD model in Ansys Fluent can simulate both static and low frequency electromagnetic fields. This capability is essential in the design and analysis of devices like electric generators and transformers. Coupling with fluid flow and heat transfer. The MHD model allows for the coupling of electromagnetic fields with fluid flow and heat transfer. This is particularly useful in the design and analysis of devices like magnetohydrodynamics devices and cooling systems in nuclear reactors. Material properties. Fluent allows for the specification of electric and magnetic properties as a function of field variables. This capability enables the simulation of nonlinear phenomena like magnetic saturation and temperature-dependent electrical conductivity. Fluent provides a wide range of boundary conditions for the MHD model, including electric potential, magnetic potential, and current density. This allows for a high degree of flexibility in the simulation of different devices. In summary, the MHD model in Ansys Fluent provides a comprehensive set of capabilities for the simulation of electromagnetic fields, their interaction with fluid flow and heat transfer, and the specification of material properties and boundary conditions. These capabilities make Fluent a powerful tool for the design and analysis of a wide range of devices and systems. Let's enter the Ansys Workbench software. Ansys Workbench is a powerful software suite that includes tools like Design Modeler, Space Claim, and Discovery. If you drag the geometry to the project schematic window and right click on it, here you can see the Discovery, Space Claim, and Design Modeler. And also Fluent Meshing, Ansys Meshing, and Fluent Meshing. It offers advanced geometry modeling capabilities for creating, modifying, and managing 3D models with precision. Ansys meshing and Fluent meshing are well known for producing high quality mesh using advanced algorithms, enabling professionals to simulate complex fluid flow problems with confidence. Okay, now I want to enter the Ansys Fluent software. Here I drag it into the main window, right click on it and edit. Here I use a parallel simulation, and after hitting the start, the Ansys Fluent software will be loaded. Are you ready to explore a vast area of mission options that will leave you amazed? Our software offers you multiple options to choose from, each tailored to meet your simulation needs and elevate your user experience. But that's not all. We provide you with advanced mesh quality checking tools that are nothing short of impressive. With these tools, you can gain a complete understanding of your simulation's accuracy and identify potential issues before they become major problems. This gives you the freedom to concentrate on achieving the best results for your project without worrying about the accuracy of your simulation. With our top-notch meshing options and quality checking tools, you're sure to experience the ultimate simulation software experience. Here, you can check your mesh file, and by this option, you can report the quality of your project. Okay, as we haven't imported the project, we need to import it first. Case file, and from the location, magnetic field, it is .cas, and that's it. Okay, this is the geometry of the project. And now you can check the mesh of the simulation and also report the quality by displayed by different parameters. Are you ready to take your simulations to the next level? Look no further than Fluent. While the software is renowned for its advanced meshing capabilities, that's just the beginning. With Fluent, you'll have access to an array of powerful tools for visualizing geometry, mesh, and graphical results, including contour, vector, and streamlines, and also plots. These tools are not only highly intuitive and customizable, but they also provide a thrilling way to interact with your data, gain deeper insights, and make better decisions with Fluent, your key to unlocking superior atoms. Okay, here you have tools for displaying your geometry, disabling and enabling any of the boundary conditions you have. And also you can take a look at elements of the geometry. Ansys Fluent is a widely recognized software that offers a broad range of versatile models to address a wide variety of physical phenomena. This software boasts an impressive suite of turbulence models. Here, by double clicking on the models, here you can see all the models available in this software. The software boasts an impressive suite of turbulence models, including Reynolds average Navier-Stokes or RANS, large eddy simulation, and direct numerical simulation or DNS. Multi-phase flow simulations are enabled through the software's Eulerian, Lagrangian, and volume of fluid models. Furthermore, Ansys Fluent incorporates heat transfer models, including conduction, convection, and radiation, to provide a comprehensive solution for CFD simulations. The software also offers various combustion models such as finite rate, eddy dissipation, partially premixed, and premixed to aid combustion simulations. Additionally, Ansys Fluent provides species transport and reaction models for chemical species simulations and various spatial models like acoustics, porous media, and discrete phase models. Ansys Fluent's impressive array of features and functionalities makes it a comprehensive and reliable tool for CFD simulation. Okay, here as you can see, the last option is the MHD model. The magnetohydrodynamics model, or MHD, is a powerful tool designed for simulating the behavior of electrically conductive fluids in the presence of a magnetic field. It couples the Navier-Stokes equations with Maxwell's equations to solve for the fluid flow, electromagnetic field, and their interaction. The MHD model in Fluent allows users to specify the electrical conductivity of the fluid, the magnetic permeability, and the electric potential of current density on the boundaries, providing flexibility in setting up complex MHD problems. It can handle both low magnetic Reynolds numbers and high magnetic Reynolds numbers. This makes the MHD model in Fluent suitable for a wide range of applications, from fusion reactors to electromagnetic pumps and metallurgical processes. Okay, here at the first tab we have the solution control tab. Here we can see the option solve MHD equation. This option allows you to solve the magnetohydrodynamics equation. MHD is the study of the magnetic properties of electrically conducting fluids, and the MHD equation is a conservation law that describes the flow of such fluids. Then we have the include Lorentz force. The Lorentz force is the force on a charged particle due to electromagnetic fields. If this option is checked, the Lorentz force will be included in the calculation. Include Joule heating. The Joule heating, also known as a resistive heating or ohmic heating, is the process by which the passage of an electric current through a conductor produces heat. If this option is checked, Joule heating will be included in the calculations. Okay, then we have the boundary conditions tab. Here you can see that for the cell and wall zones, you have some types. The part solid is kind of solid, and part fluid is selected as fluid. And here we have the wall boundary conditions. For each of them, we have 4 options: insulating wall, conducting wall, coupled wall, and thin wall. In case of insulating wall, an insulating wall is a boundary condition in which the wall is considered as a perfect insulator. This means that it does not allow any heat to pass through it. In Ansys Fluent, this is represented by setting the wall heat transfer coefficient to 0. This condition is typically used in situations where the effect of heat transfer through the wall is negligible compared to other heat transfer mechanisms. A conducting wall, on the other hand, is a boundary condition that allows heat to pass through it. The rate of heat transfer is governed by the wall's material properties, particularly its thermal conductivity. In Ansys Fluent, you can specify the wall heat transfer coefficient to represent the rate of heat transfer through the wall. A coupled wall. A coupled wall is a boundary condition that models heat transfer between 2 adjacent fluid zones. This is typically used in situations where you want to capture the effect of heat transfer between 2 fluids separated by a thin wall. In Ansys Fluent, you specify a coupled wall by selecting the coupled option in the wall boundary conditions. And the last one, thin wall. A thin wall is a special type of boundary condition that models a wall with a finite thickness but without resolving the wall thickness in the mesh. This is used in situations where the wall thickness is small compared to other dimensions in the problem, and you want to capture the effect of heat conducting through the wall without the need for fine mesh. In Ansys Fluent, you specify a thin wall by selecting the thin option in the wall boundary conditions and specifying the wall thickness and thermal conductivity. Each of these boundary conditions is used in different scenarios depending on the characteristics of the wall in the physical problem you are trying to model. Okay, then we have the external field B0. And here the first option is B0 input option. Okay, for this option, we have patch and import. This option allows you to specify how you want to input the external magnetic field B0. First, we have the patch. This option lets you specify the B0 field in different regions of your model. You can define different values of B0 for different patches in your model. And also the import option allows you to import the B0 field from a file. The file should contain the B0 field data in a format that Ansys Fluent can interpret. Okay, then we have the field type, DC field and AC field. Here we have selected AC field and its frequency. It is selected as a moving field, and here you can also enable the sinusoidal or square wave form. Here we have the B0 component. This option lets you specify the mean values of the B0 field component in the X, Y, and Z direction, and their amplitude and phase. I am very delighted to discuss the powerful pressure velocity coupling schemes that Ansys Fluent offers. Ansys Fluent offers powerful schemes. The simple algorithm is the perfect. Here you can see the pressure velocity coupling schemes by selecting the scheme. The simple algorithm is perfect for steady state calculations, while the simple C scheme offers faster convergence. The coupled scheme is ideal for high speed compressible flows, and the piezo scheme is great for transient simulations. Each of these schemes in Ansys Fluent brings its unique strengths to the table, providing you with a wide range of solutions for your simulation needs. And after that, you have uh, various tools of first order, second order to uh, third, and other different options for each of the equations. Okay, then we have the initialization. By double clicking on it, you can see that we have hybrid and standard initialization. The standard initialization method initializes the flow field by setting flow variables to user specified constant values throughout the computational domain. This method is often used when you have a good estimate of the flow field. On the other hand, the hybrid initialization method initializes the flow field by interpolating values from the boundary conditions. This method is particularly useful when you do not have a good estimate of the flow field. It can provide a better starting point for the solver, especially for complex flows leading to faster convergence. And finally, we have the run calculation. Ansys Fluent's iterative mode is a critical process that solves complex problems step by step. It's useful for nonlinear problems, continuously refining the solution for better accuracy and control. Okay, after running a simulation, Fluent provides a range of options to analyze and visualize the results. You can generate contour plots, vector plots, and path lines, which help in understanding the flow patterns in a fluid. Fluent also allows the creation of um, animations which are useful in presenting and understanding transient behavior. Moreover, it offers quantitative processing tools that include calculations of derived quantities, report definitions, and monitors. Okay, here you can see the mesh, contour, vector, pathline, particle tracking for different projects. For example, here we can open a contour. We want to see the variation of pressure. That's it. You can zoom in, zoom out, or move the geometry. And that's it. This tool allows users to extract specific data of interest, such as forces on a body, average temperature in a region, or flow rate through a boundary. Here you have the report section to report the different parameters on each section of the project. Fluent's post-processing capabilities are highly customizable, allowing users to tailor the output to their specific needs. Overall, Ansys Fluent's post-processing capabilities are essential in interpreting the results of CFD simulations, enabling users to gain insights into their simulations and make informed design decisions. Remember, the best way to learn about these capabilities is to use the software and explore its features. Here I'm gonna show you some of the results extracted from the software.